Hello and welcome. I am Muhammad Ali Naim, a PhD student from Bangladesh University of Engineering and Technology. I will present our research on a multi-objective meta-heuristic approach for accurate species tree estimation. Here is the outline of my presentation. In the introduction, I will give a background of our problem, the challenge we aim to address, and our problem formulation. Then I will briefly discuss our algorithms, followed by the experimental results and conclusion. In biological studies, a species tree or phylogenetic tree represents the evolutionary history among a set of related species. Here we show an example where a species tree relating 4 species are shown. Now, if we sample a gene from each of these species and draw the evolutionary relationship, then it will be called a gene tree. Here, a species tree is shown using block diagram. And here, each of the line diagram shows a evolutionary relationship of a single gene. As different regions of the genome can evolve differently, we can see the gene tree as a cloud of, we can see the species tree as a cloud of gene histories. Now a gene tree can disagree with its containing species tree. For example, here in the species tree, B and C are sister species, but in the gene lineage, C is more close to D than B. Due to such discordance, the task of estimating species tree from multi-locus data is complicated. To estimate a single gene tree, we arrange the sequences of different species into a matrix and apply sequence-based statistical approach to estimate the gene tree. Now the question is, how should we estimate the species tree? A common approach is concatenate all the gene sequences into a supermatrix and then apply a statistical method to infer the species tree. But as it assumes that all genes follow the same history, it can return incorrect trees with high confidence. An alternative approach is summary method, which infers a single gene tree from each gene sequences and then summarize those trees in the best possible way to infer a species tree. As it considers gene tree discordance, these methods are increasingly popular. To evaluate the performance of a species tree estimation method, we need to compare its output tree with the true species tree. There are several possibilities. One of them is FN rate, which means false negative rate, which expresses the percentage of ages present in the true tree but missing in the estimated tree. In this figure, the red age is a false negative age. But we need to keep it in mind that this measure is not the fitness criteria of the estimation method. If we look at the existing summary methods, we see that they optimize a single criterion, which is a statistical consistent estimator of the true species tree, to estimate the species tree. For example, Astra, which is one of the most popular method, maximizes quartile score. MPEST maximizes pseudo likelihood, and Stellar maximizes triplet score. But in practice, we have limited number of gene trees and there is gene tree estimation error. So such method may overshoot the criteria they try to optimize and thus may deviate from the true tree with respect to FN rate. In this study, we aim to improve the performance of summary methods using multi-objective meta-heuristics. A multi-objective meta-heuristics simultaneously optimize more than one objective functions. Here, we see a multi-objective task with 2 decision variables and 2 minimization objectives F1 and F2. A solution can be represented in the objective space using its objective values. In this context, a solution is called dominated by another solution if it is not better in any objectives and is worse in at least one objective than the other solution. Here, these gray boxes are dominated solutions, and these colored boxes are paired solutions or non-dominated solutions which cannot be dominated by any solution. Here, the red line, which is composed of all paired solutions, is called the paired front. So, the target of multi-objective mathematics is to sample the paired front. In this study, we formulate the task of estimating a species tree using a multi-objective task. Here we are given a set of estimated gene trees, and we need to generate a species tree that best summarizes the given gene trees. As in, to quantify the goodness of summarization, we simultaneously optimize three objective functions, which are quartet score, pseudo likelihood score, and triplet score. In this study, we treat each of them as a minimization criteria. But unlike a classical multi-objective meta-heuristic algorithm, our goal is not to effectively sample the paired front because of these two issues. Issue one is over-optimizing a particular objective may lead to deviate from the true species tree, as we said earlier. And issue two is a dominated solution at an early stage may evolve into an accurate tree at a later stage, but a classical multi-objective meta-heuristics try to discard a dominant solution. So we need to develop a customized algorithm to tackle our problem. NSGA2, which stands for Non-Dominated Sorting Genetic Algorithm 2, is one of the most widely used multi-objective meta-heuristics. It gradually evolves a set of solutions towards the paired front. At each iteration, it generates an offspring population using genetic operators. Then it selects the required number of solutions for the next iteration using non-dominated sorting and breaks ties using the crowding distance if necessary. Crowding distance measures the sparsity of a solution in the objective space. We develop an algorithm which we call summation of normalized objective space genetic algorithm, in short SNOGA, by modifying NSGA2. In SNOGA, we avoided the non-dominated sorting of NSG sorting as we found it related with the two issues that we mentioned earlier. Here is the algorithm of our SNOGA. In short, instead of the non-dominated sorting, we use sorting based on SNO, which stands for summation of normalized objectives, to pick solutions for the next iteration. This is our SNO function, where we normalize each objectives using the maximum and minimum values observed so far, and then adds them together. We use two-normal selection based on SNO value to intensify the effect of SNO function. And we use crowding distance concept of multi-objective optimization to keep some, to pick some sparsely spaced solutions in the objective space, and used random selection to ensure their participation in the objective space. Here is our experimental setting. In this study, we selected 3 simulated data sets, each having 10 replicates numbering from R1 to R10. In this context, a replicate means a randomly generated instance of the simulated data set given the model condition. We used the same parameter configuration for both NSGA2 and SNOGA, and we incorporated popular tree rearrangement strategies as genetic operators. Here we show our observation on overshooting, which effectively motivates us to conduct this study. Here the top row shows the ratio of quartet score of true species tree and astral estimated tree for each of the 10 replicates of each data sets. This ratio is ideally should be 1, but we see that in most of the cases this ratio exceeds 1, which means which implies the over optimization of the criterion. A similar phenomenon can be seen in case of pseudo likelihood score and triplet score in the bottom row and in the middle row and the bottom row respectively. Now we try to see the behavioral difference between NSGA2 and SNOGA. So we plotted the values of individual objectives and the FN rate across different generations. The top row shows the result for NSGA2 and the bottom row shows the result for SNOGA. We see that NSGA starts to degrade FN rate after a particular generation, despite the continuous improvement of one or more objective values. On the other hand, due to our modification considering the two issues, SNOGA restricts the improvement of individual objectives after a certain generation, and it ensures the improvement of FN rate across generation. In this figure, we compare the multi-objective meta heuristics with the 3 summary methods. So we show the average FN rate with standard error bar averaged over 10 replicates for each data set. We see that SNOGA achieves at least around twice accuracy than the 3 summary methods, and it achieves at least 1.4 factor accuracy gain than NSGA2. So we can say that the modifications we made into the SNOGA helps it to perform better. In conclusion, we'd like to state that a carefully customized multi-objective meta-heuristics can deal with practical model conditions with limited numbers of estimated changes, and it can generate a tree space containing highly accurate species tree compared to the trees estimated by optimizing a single criteria. At present, our studies has some limitations. For example, our meta-heuristics generate a lot of alternate solutions, and its runtime has been increased due to external dependency with the existing summary methods. We are working to fix this limitation so that we can effectively tackle biological datasets. I would like to thank IEEE division from Government of People's Republic of Bangladesh for supporting me with the IEEE doctoral fellowship. Thank you.